Okay, I should get started. My name's Greg Waynes. I work at Wind River. I'm an architect on their Titanium Cloud product and also a member of the new Starling X open source projects that have been announced this week. This lightning talk is to talk about some upstreaming work that we've done in OpenStack Masakari, which is all about high availability VMs, and basically some enhancements that we've done to their VM instance monitoring in order to leverage, by leveraging a direct host to guest interface. First, just a little bit about Wind River. Wind River is its heritage is in embedded software. We've got software in billions of devices across the world. Most of them in environments where the requirements have, strict high availability requirements, safety requirements, security requirements. So lots of devices. Basically, if you used a cell phone or had an MRI or been on a Boeing jetliner or driven a Land Rover on Mars, you've probably used our stuff. But Wind River's also got products in Internet of Things type areas as well as cloud computing, and that's kind of the area that I'm in. Wind River has a Titanium Cloud product. It's basically an OpenStack-based private cloud offering that differentiates on high availability and high performance, both data path performance, as well as ensuring high compute performance for the VMs that it's hosting. And we're actually deployed in many different market segments, both networking, like telecom type applications, as well as in a number of industrial and control type areas, energy control type plant type stuff, medical, manufacturing, a lot of different industrial control. So besides high availability and performance, we've got other features like ease of installation, commissioning. We've done a lot of work in that, a lot of security features, which are basically, table stakes for a lot of the industrial control type stuff. Okay, so the real stuff of the presentation. Just first a bit of background. OpenStack Masakari is a relatively new project. I think it really just came under the big tent in maybe Queens, maybe really just officially Rocky. But it's all about providing high availability for virtual machines. So the architecture, right off their read the docs page, basically they have a set of Masakari monitor agents that run on the compute, and they monitor a variety of things. They monitor host connectivity to the compute nodes. They do critical process monitoring of the OpenStack service infrastructure. And they also do monitoring of the instances of the VMs themselves. And if they detect a fault, they'll report the fault up to the Masakari API and Masakari engine that's running on the OpenStack controller. And then the Masakari engine, based on the fault type, has the smarts to do recovery of the particular virtual machine. So for example, in the case of a VM being in a bad state, according to libvirt, it'll do a restart of the VM by doing a Nova stop and start. Or if a whole host has gone down, it will evacuate the VM to recover to a different compute node in order to recover the VM. All right, so basically, the enhancements that we did to OpenStack Masakari were really in the area of improving or extending the instance monitoring. The instance monitoring that they have today is good. It's based on it, but it's a black box type monitoring capability. It basically, listens to the libvirt events in order to understand the state of the QEMU process that's hosting the VM. And reports that up. So it's good. It's black box monitoring, though. There's a lot of faults that can occur inside the VM that wouldn't detect. So what we thought we'd do was to be able to enable some white box monitoring to actually kind of reach into the VM, check the state of the VM, check the state of the the OS and the app, even the application inside the VM. in order to detect additional faults that still could be recovered through the same Masakari recovery techniques that the Masakari engine has. So what we did was we decided to leverage, there's actually a QEMU guest agent, which is part of the upstream open source QEMU agent packages, that if a VM includes that QEMU guest agent in its image and initializes it, there'll be a guest agent running inside the guest, listening, with a socket and listening to a virtual serial interface, which is connected to the host, and it'll just be listening for commands from the host. And so the QEMU guest agent has a lot of kind of standard built-in commands, like there's simple ones like guest ping. You can look at disks and file systems and memory. You can even send like completely arbitrary commands that get run in a shell in inside the VM. So what we did, it turned out that actually Nova already supported an image property that indicated that a guest was running a QEMU guest agent and would launch the VM with the appropriate virtual serial interface through QEMU. So we basically leveraged that, and we extended the Masakari instance monitor so that it would detect whether VMs that were being launched on that compute actually had the QEMU guest agent socket open towards it. And then if it did, we'd regularly monitor it by sending, initially all we're doing is sending an initial guest ping, but that indirectly can detect a lot of faults within the VM, like if the guest OS is hung, or it's not scheduling processes correctly, or if there's severe resource exhaustion going on, then you're not going to get a guest ping response back, and you'll indirectly detect some of these faults. And then we'd, again, along with all the other Masakari monitors, we'd report that up through the Masakari API, and then have the Masakari engine basically do a recovery process of for example, a VM restart through a Nova stop and a Nova start. So, and even this capability could be extended in the future to actually detect more application faults. But yeah, so the status of this is the blueprint is and spec are approved. We're in the process of reviewing the code and getting that submitted as well. The last slide I had was really just to kind of talk about what other possibilities there would be in using a host-to-guest interface between the OpenStack platform running on the compute node and the VM guest. So some other possibilities that would help in high availability of VMs. The first two really are about introducing something like a Nova proxy to intercept Nova commands that are potentially disruptive to the VM, like a stop start or a reboot or a pause or resize, and notify, at the very least, notify the VM that this action is about to occur so that it can gracefully prepare for the action, maybe close files or shut down protocol connections gracefully or that sort of thing. The other thing you could do is take it even one step further and allow the VM to actually knack or warn the OpenStack platform that of a problem, like effectively knack the operation. And a use case for that would be like, say, if my, that operation being disrupted is potentially going to take my service, cause a service outage. So I could be a VM in a one-for-one sparing model. The Nova stop that the guy entered might be for my active VM, but obviously OpenStack isn't aware of the active standby status of the application. So if the VM's the active one, and then that VM actually knows that his peer VM is not in sync and ready to take over, there's the option that he can knack, and the OpenStack platform, if it is aware, can actually just provide an error message back to the user. And the user can always, I know the way we've implemented this in our solution is that the user can always do a force to override it, but it's a way to kind of hook into the semantics of the application. Some of the other ideas are, we could even provide a lightweight broadcast notification between VMs, say of the same server group, in order to provide an alternate messaging path between VMs. Obviously, when a VM's fully up, it's using the virtual networking of Neutron to communicate between VMs. But something like this could be up super quick because it's just a virtual serial interface on the host. It could even be used as an alternate path to prevent split brain scenarios in a one-for-one sparing between two VMs or something like that. And then finally, another use case would be, there are some things that the platform might try to do. An example would be something like vCPU, resource scaling. There are scenarios where the platform can't do it completely on its own. It needs some interaction with the guest OS. vCPU resource scaling, dynamic scaling is an example of that. Like even though OpenStack or Nova would assign or remove a vCPU from the VM, really to make it work correctly, the VM guest OS needs to properly be notified of that event and properly offline or online the vCPU. So these are just some ideas that would kind of extend or leverage the same type of technology, the QEMU guest agent technology that we've done to do the introspective instance monitoring in Masakari. All right, I think that's it. Any questions? Yep. Oh, sorry, like a false positive where the... Yeah, well, the connectivity is between the OpenStack platform and the VM is like the OpenStack, the Masakari monitors run on the compute node that's hosting the VM, and it's just a virtual serial interface. So it's direct. There's no equipment in the middle. Yeah, so every compute node has some Masakari monitors running on them, and in the case of the instance monitor, each Masakari instance monitor will be monitoring all the instances that are just on that compute host. So it's all direct communication. Yeah. All right, thanks.